And then the next song that we'll be playing is Twinkle Twinkle Little Star.
Oh, it overlapped the song. We should reset it. Sorry about that. Yeah.
It plays everything wonderfully, it's just if there's human error, then that's a bit of an issue. Okay, you send the song in, let's try it again.
We'll first spin it a little while first.
Of course, of course.
There we go.
Alright, and then the next song that we'll be playing, the last one, is the Star Wars Imperial March.
Sure. So what we have here is we have a cross with five solenoids, one on the start button and one on the top, left, right, and bottom. If you haven't seen DDR, it's a game where there's a song and the user has to step to the beat of the song with different combinations. And this is our user interface where we select what song we want and the difficulty level, and the LCD is where we click it, and the buttons. So yeah, and the bricks are here because the solenoids are only 10 pounds of force, which the game board is used to having like a human step on it, which gives much more than 10 pounds. So we needed something to weigh it down, so we got the full 10 pounds of force. Even then, sometimes we've had trouble with it not detecting the touch, but you know, right now it's perfect, so it should work. Robot? We're taking volunteers for Just Dance, Lady Gaga. Die. Okay. Okay, thank you.
We have this and these, the top 6 sensors represent the fret sensors and where you're holding them. We have the strings.
So you can see it. You can see the force sensors over here.
This one's supposed to be that one.
Yeah. And so as we play the same string with different fret, it'll play different notes, different frequencies. And
then if you can see over here, it's kind of hard to see, but you have the LEDs indicating how hard you press it. So, not the perfectly tuned guitar, but guess it'll work for.
yeah.
So here's a video of approximately what that looks like when you have it working. So we can do that.
So it presses the button, but it doesn't press enough force to actually
punch it. So it's going to go and, it goes and, it hits the button, but it doesn't have enough force because the arm just, gets flexed back. So
the less human fingers is surprisingly strong.
Yeah.
So this is actually going to 4 different stages. It goes to 4 different corners after.
First up on that corner, then on the right corner and bottom corner is that corner.
It actually beeps when it gets to that state. Not connected.
What happened?
So here we have Rob. He's calibrating with the Connect. So now we have his coordinates. And these numbers on the screen show the velocities and the camera position.
So you can see how as I move my hands down, I can position the camera up. And as I move it forward, I can make it go forward. So I'm trying to look just at the
Yeah. Nice.
Good.
There's no backup. Oh, camera. Can you make the camera up?
Oh, there's me.
Are you able to go backwards? Or just
Yeah. So.
But then you can't see where you're going though.
Yeah. And yeah, I didn't really demonstrate being able to look around too much. You can look wherever you want. So we have it tilted down because it's you need to see right in front of you. So unfortunately, you can't see that far ahead. But it's overall much more useful for navigating around backpacks and stuff. But yeah, if we keep the hands down here, we can sort of see more of the room and see what's going on. So I'm bringing them back to me now. My faithful robot.
Yeah.
Oh, sure.
That's good enough.
So basically, it's sending it through this XP that's connected to the computer, which we're using Python to open a serial connection, and then it communicates to the one on the chip. So in real time, what would be happening was we'd have a server on land and these robots out in the water, and the XP server will be communicating with each of the individual robots. And then we can also toggle a compass and get readings out of the compass. Okay, this is just debugging info, but so we get the compass heading reading. So the GPS doesn't work indoors because it doesn't receive a satellite signal, but it works in a similar way to this.
So those two are two VIs, each running on one of the robots, and the one on the image on the bottom is a simulation of what's going on. And so the dot that's going around the circle is the position of the robot, whereas all the white blobs are estimates of where the Tetra is. So those are the particles.
Oh, I see.
Yeah, the red is the middle of it, whereas the yellow, there's a cross that signifies where the actual location of the Tetra is. And the top graph is a graph of time versus error. To the actual position. And you can see those plots over there. The error plots are sort of oscillating. That's not typically a behavior department filter. But they tend to oscillate around a point, again, 2 to 4 centimeters. Yeah. Over the actual distance. So every time you see that little circle here, that's when a robot takes a reading. Yeah, it shows you how far away it thinks it is. Yes. So you'll notice that it doesn't always actually correspond to where the Tetra is. It's sometimes off, it's noisy. So a lot of this program is this project is about robustness and figuring out that despite the noises of the sensor, despite the fact that it doesn't know which direction it's in, there's still algorithms and methods that you can communicate in real time, get a better estimate. And there's a better estimate on that graph we take the centroid of the two centroids to get a better idea of where it is.
So when it gets within a certain range of the Rovio, it's been programmed to slow down and hopefully stop. If it bumps into it, it'll go into the normal backup and turn to. At the time we programmed this, we were expecting the range to be much larger for the sensors, so it would have to avoid table legs to catch up to the lead time.
We kind of keep the distance so far because it ends up, if it faces the front of it, it'll crash into it if it gets too close. So yeah, basically that's why it's following it so far and it keeps stopping and not come back.
Also just because of noise, the distance estimate tends to be noisy, so especially because it's a 1/r² relationship, as you get farther away it gets quadratically worse, the estimate does.
It also has a collision detector. for the follow? Well, we're trying to follow by about 2 or 3 centimeters or so from behind it, but we're really right now. Still on the wire. Oh, the battery ran out again.
Yeah.
The Robio battery died again. So.
Okay, so this happened because something is stuck in the data flow because it's rushing around.
So one of them should have actually stopped and the other one would have
Yeah.
gone around.
Something like that. But I think this computer is crashing over there.
So that was solved.
That's worse. Okay.
How do
As
you
soon as
just-
we had received.
How do you decide which one stops?
Okay, so we just arbitrarily choose one to stop. So it's reached the destination. So what more data? 2 different paths. Okay.